So in this video, we're going to do some revision about the AQA measurements and their errors module. Now, this doesn't really sound exciting, but it's actually probably one of the most important topics in A-level because you need to know how to look at quantities and units when it comes to every single calculation. And also, even at the very end of year 13, you need to know about some of these practical skills which you're going to be assessed on in the exam. Now, don't forget, you can, of course, subscribe on YouTube to find hundreds more videos. And also you should go to alevelphysicsonline.com where we can find everything organised by exam board and by topic. So there's loads and loads of stuff there that you can sign up to really help you. Right, let's begin. So the first thing in this module is looking at what we call the SI units. And this international system of units just means that whichever country you're working in, we always use the same format. Now, the first thing we can think about are what we call base units. And there are some quantities that we can consider. So these are kind of some of the kind of basic things. Now, the quantities include things like mass, length, time, the amount of something. That doesn't really have a shortened symbol. We also have temperature. Sometimes we use a capital T for temperature. Sometimes we use a theta, which is a bit like a Greek letter T. So either of these can be used to represent temperature. And then finally, we have current. Now, all of these quantities, they are things which have a size, they've got a number, and they've also got a unit. So the units we might consider include kilograms for the mass, metre for length, time in seconds. The amount is in moles. But to be honest, this is kind of more chemistry. We don't really tend to cover that in physics much. We should measure temperature in the Kelvin scale, the absolute temperature scale. And then finally, current is measured in amps. So these are the base units that you really need to consider. But there's often lots of other things we're measuring, things like forces, things like energy. And what we also then have is we have our derived units. Now, an example of a derived unit might be velocity measured in meters per second, or it could be something maybe like acceleration, which is meters per second per second. Now, these ones here are derived from some of these base units. And that kind of sounds fairly straightforward. But let's consider the force. How can we actually measure force in its base units? Well, we know that the force is equal to mass times acceleration. This is just one of the many equations that we can use. Now, we measure mass in kilograms, and acceleration is metre second to the minus 2. So this is now a derived unit. Effectively, 1 kilogram times 1 metre times 1 per second is the same as 1 newton, which is a shortened unit, but we can also express newtons in terms of the base units. We could do the same for energy. Now, it doesn't really matter which equation we use, but let's look at perhaps the energy of something in its kinetic store. That's going to be equal to a half mv squared. Now, because half is just a number, that doesn't have any units. Mass is in kilograms. V squared, well, it's going to be m squared s to the minus 2. So we've just squared ms to the minus 1. And now what we have is our derived unit for energy. And often we shorten this to the joule because otherwise you'd have to be writing this down all the time, and that's just too much. So here are some of the derived units that we need. Now, the problem is, the great thing about physics is we look at really small things and really big things. And sometimes just measuring things in kilograms or meters isn't quite enough. So what we have as well is we have our prefixes. I can never remember if it's prefix or prefix. I say prefix. And this just allows us to represent really big and really small numbers. So going from big to small, we have big things, which are tera. Then we've got giga, mega, kilo. And going smaller, we've got milli, micro, nano, pico, and femto. And if we think about the size of these, well, a tera is times 10 to the 12, giga is 10 to the 9, and so it goes down, decreasing by 10 to the 3 each time. Now, we have other things as well. We have things like center, which is 10 to the 2, so things like centimetres, that's really useful. And I suppose what you've got to think about is when it's most applicable to use these. So it might be that if we're talking about things like a wavelength, we might be using 10 to the minus 9 because we've got wavelengths in nanometers. We might be using femtometers when we're looking at the subatomic scale and things like the strong interaction. So these prefixes are really useful, and you'll develop them just by doing lots and lots of physics. Now, the other thing with these units is that we can measure energy in kilogram meters squared s to the minus 2, but normally we use joule for energy. But sometimes we're looking at really small energies and electron volts are used, and other times we look at things like household electricity, where it's more appropriate to use a kilowatt hour. Now these are just different units rather than the SI unit, and it's sometimes worth actually understanding where these come from. So the electron volt, effectively this is the energy required to accelerate an electron from rest through a potential difference of 1 volt. And later on when you do stuff on electricity, we start to realise that things like potential difference is the amount of energy per unit charge. So if I just take this equation here, we can say that energy is equal to QV. And if we're thinking about an electron, well, the charge on an electron is the elementary charge, which is 1.60 times 10 to the minus 19 coulombs. Now, if it's an electron, it's actually a negative value, but we're just thinking about the size of that, which is 1.6 times 10 to the minus 19. And if we multiply this charge by 1 volt, then this gives us an energy equal to 1.60 times 10 to the minus 19 joules. So 1 electron volt is 1.60 times 10 to the minus 19 joules. So a really, really small amount. When it comes to looking at electrical power, we can say that the energy transferred is equal to the power multiplied by the time. Okay. Now, here we've got an energy of 1,000 watts, so that's the power is equal to 1,000, and the time over a period of 1 hour is going to be 60 times 60 seconds, which is 3,600. And that means that we then come up with a number of 3.6 times 10 to the 6 joules. So what we can also say is that 1 kilowatt hour is the same as 3.6 times 10 to the 6 joules. Okay, so these are just two ways of having other more appropriate units to represent the normal kind of standard SI unit. Now, this stuff here, you're going to be doing lots and lots of practice, and just basically by doing AS physics and then all the physics in year 13, by the time you get to your exams, all of this will seem like second nature, using prefixes, thinking about the kind of base units, and maybe some of the derived units as well. But now one of the problems with measurements is that there are actually quite a lot of limitations, because we're not just thinking about a theoretical thing where we have perfect numbers. We're not in the maths classroom. Instead, we're in the real world. And when you actually take measurements, we often have errors. And the whole point in doing practical work in physics is that you can maybe start to understand different ways to minimise the errors. Now, there's really two sort of categories. Some errors are what we call random, and some are what we call systematic. Now, perhaps we took some data and we got values of maybe 1.11, 1.12, 1.11, 1.13, 1.14. That's the kind of stuff you might get, and it doesn't matter if this is length or time or current or whatever it might be. And basically what we have is there's some kind of spread of this data around whatever the true value is going to be. And basically this is just something that happens in real life. It's just very, very hard, and actually be a bit suspect if you got values of 1.11, 1.11, 1.11, 1.11. Okay, so what we find is that when you repeat stuff, we find that there's a very small spread of your data around what the true value is going to be. And the way that we reduce this is we reduce it by repeating, by repeating, by repeating. Effectively, the more times you do that experiment and then get a value for the mean, the better the final value you're going to get. Now, you obviously do this in every single practical. It's probably been drummed into you since year 7 when you have to do your repeats. But this is why we repeat stuff, to kind of reduce this random error. But sometimes what we might get are systematic errors. And the thing is, you don't always know you've got a systematic error maybe until you plot a graph. And basically what we have is a difference from the true value, but it's maybe by the same amount each time. And the reason you get a systematic error is often because of you, because you're maybe doing something wrong. It might be that you're using an instrument that's maybe not set up correctly. It might be something to do with the method. Okay, so maybe there's a mistake where every time you do the same error, and that means all of your results, rather than being near the true value, they're all away from that true value. So what can you do to kind of get over this systematic error? Well, what you can do is that you can do the experiment perhaps using a different method. So it might be that you're the person replaced and somebody else comes to replace you to measure time. It might be that the setup that you had originally just doesn't work. So to overcome the systematic error that you might find, what you can do is address the method, maybe use better instruments, maybe just take care of your technique, and that will reduce this. But the thing is, we can never get rid of errors completely. Now that's fine, because what we can do is we can obviously think about the best way to do our experiments to make sure that certain things happen. And there are certain keywords, if I just put them over here, there are certain keywords that you need to know what they mean. Okay, so the first one is accuracy. Okay, and this is basically how close your result is to the true value. So perhaps you're measuring the acceleration due to gravity and your true value is 9.81. So that's the true value. And if you get an answer which is 5.6, then actually your result isn't that accurate. I guess some of the problem is that how do we know what the actual true value is? Because often that's had to be carried out in experiments as well. But basically, accuracy tells us how close your result is to the true value. Now, something which sounds familiar, or similar, sorry, is precision. And this is really how close your readings are together. So this one over here, where we had lots of values which were quite close to one another, these are precise readings because they're all quite close to one another. And what you find is that if you've got an experiment which is repeatable, then that means that you get similar results. So you might do the experiment, you could do it an hour later, and you would get the same values when you record these measurements. But something which sounds similar is something which is reproducible. And if an experiment is reproducible, that means that other people, maybe using a similar method, would get similar results to you, or maybe you get the same result by using a different method. So repeatable is you doing the same thing and getting the same values. Reproducible means that other people do it, maybe another group, or maybe you're doing it on another day with a different setup of equipment and you'd still get that same value. And the other thing you need to know about is resolution. And this is basically looking at the instrument that you're using. So for example, if you're using a millimetre ruler, maybe a 30 centimetre long ruler, then the resolution would be 1 millimetre because it could measure to that nearest 1 millimetre. So this is really due to the scale of the instrument that you're using. Now the thing is, when you're actually doing the experiment and you're trying to make sure that your results are precise, they're repeatable, they're reproducible, you've got high resolution instruments to try and get an accurate value, there are still going to be errors introduced into your work. And what we call this is uncertainty. Now, uncertainty is not a bad thing. It doesn't mean that you're doing the wrong thing. It doesn't mean you're making mistakes. But it's basically something that we have to account for and try and actually minimise in our practical work. Now, the way that AQA use it is they use a triangle for the sort of delta. And this is what they use to represent the absolute uncertainty. And this represents the absolute uncertainty in a reading. So for example, perhaps you're measuring the length of something, then we'd measure that uncertainty maybe perhaps as plus or minus 1 millimetre. Or perhaps you're looking at temperature and you're thinking about plus or minus 1 degree Celsius. Now when you're doing this, because it's the absolute uncertainty, it also has units as well. So an example of this might be that you're measuring something and the length is 29 millimetres. But, and we'll come on to this in a second, we might find that it's got an absolute uncertainty of plus or minus 1 millimetre. Now, the other thing that we can do, and actually this is sometimes more useful, is we can look at percentage uncertainty. And the symbol that AQA use for this is an epsilon, this kind of sort of curly E. So basically this tells us about the percentage uncertainty in a reading. So we might be talking about perhaps plus or minus 2%. So absolute has units, percentage uncertainty is just a percentage. Now the way that we calculate percentage uncertainty depends upon the absolute uncertainty, but this is where AQA talk about the difference between readings or measurements. And when they talk about a reading, what they're talking about is where you make a single judgment to come up with your measurement. Now, a good example of this might be if you've got a thermometer, because basically you put your thermometer in and then you just take your reading and it might be 10 degrees Celsius, for example. And basically you don't know where that kind of column of mercury or alcohol begins. You can only read off one data point. So this works if you've got things like thermometers. It also works if you've got a digital meter, so maybe an ammeter, a voltmeter, or something like that. You don't know the 0 point, but you plug it in and it might say 2.85 volts. Okay, and what you're doing there is you're just looking at a single judgment. When you've got measurements, and this is kind of quite specific, is where you have to make two judgments. And a great example of that might be where you have a protractor, because what you have to do is you have to judge where you start your reading from, and you have to judge where the end point is. And that means effectively there's going to be some uncertainty in this reading and some uncertainty in that reading. So this is things like perhaps rulers for measuring length. It's got things like protractors and also analog meters. Because with these meters, effectively, there's going to be a 0 point where you have to set the dial at the beginning. Now, in terms of how we quantify that, basically, when you're looking at a reading, which is a single judgment, we're looking at plus or minus half of the smallest scale division. So for a thermometer, this would be plus or minus 0.5 degrees Celsius if you're just using a standard one that measures to the nearest 1 degree Celsius. If, however, you're using a ruler, effectively, we can judge the start point to half a millimetre and the end point to half a millimetre. And that means that when you've got two judgments, then the uncertainty, the absolute uncertainty, is going to be plus or minus the size of the smallest scale division. So with a ruler, this would be plus or minus 1 millimetres. So that's the difference between readings and measurements as far as AQA see it. So maybe we've looked at the absolute uncertainty in a piece of data. We can now start to work out the percentage uncertainty. Now, depending on the kind of data we've got, there are two different ways of doing that. So let's first of all think about if we want to look at the percentage uncertainty in a single reading. Okay, well, the way we do that is we first of all need to look at the uncertainty, which is going to be the absolute uncertainty, and we divide this by the measured value. So for the example up here, if we're looking at maybe an absolute uncertainty of 1 millimetre, and we divide that by the measured value, which is 29 millimetres, then we do 1 divided by 29, and then don't forget to multiply by 100 to make it a percentage, and it's a value of 3.44. Now, the whole thing about dealing with errors is this is just a way of trying to quantify our experimental data. And the method we use is kind of a rough approximation. So although it's 3.44827, I say that probably with this, we can say that's going to be equal to 3%. Okay, so that's how we can look at the uncertainty as a percentage of a single reading. But obviously, we want to have lots of repeated readings so we can actually reduce any random errors. And what's useful to do then is think about working at the percentage error of a repeated reading. And we do this by looking at the uncertainty. So let's imagine we have some data, just like this, so 10.5, 11.2 and 9.8. Well, the uncertainty in this data really depends upon the precision. Effectively, if we've got a massive range and a massive spread of results, it's going to be less precise and it's going to be more uncertain. So first of all, we're going to look at the range of this data, which goes from 11.2 down to 9.8. So 11.2 minus 9.8 is just 1.4. And when we look at the uncertainty, it's going to be equal to half the range. And what we're then going to do is we're going to divide this uncertainty, half the range, by the mean value. So in this case here, the range was 1.4 from smallest to biggest. Half the range is going to be 0.7. And we're going to divide that by the mean value. In A-level physics, we tend to talk about the mean. We just ignore modes and medians. So let's have 10.5 plus 11.2 plus 9.8 divided by 3. So the mean is 10.5. Oh, that's quite nice. And then we go 0.7 divided by previous answer, times it by 10, divided by 100. And this gives a value of 6.66, which is therefore about 7%. Effectively, if you've got a bigger spread of results and you get some high ones and some low ones, we're going to have a bigger range of results, which means we're going to be less certain about the actual precision or the accuracy, the precision of our data. Okay, so that's how to work out the percentage uncertainty for single and repeated readings. But actually what we tend to do in science is we often draw a graph. So let's just have a look at that. Now, I know that you know this, but let me just reiterate. When you're drawing graphs, you've got to think about choosing an appropriate scale. You've also got to think about the size as well, because if you've got a massive graph and all your data is in one corner, then your graph is just the wrong scale. You want to have your data over at least half of the graph that you've chosen. The other thing that we have on each axis is you need to put in your quantity that you've actually measured, and then have a slash, and then you have your units. So it's very clear what that graph is showing. Now, when you plot the data, you can use kind of little plus symbols, or you can use a cross. It doesn't really matter which one you're using, as long as it's clear. So after you've drawn in a line of best fit, if that's appropriate, you can see where the data point originally was. Now, something you can do is also put in error bars. Okay, so maybe this is your mean value that you're plotting. Sometimes it's also useful to put in an error bar, and that basically allows people looking at your graph, or even yourself, to actually think about, is that data good data or not? So how do you work out the error bar? Whoa, I've just drawn a lot more on here. My camera just stopped working, so I'm back in it now. I'm just going to cover what I said when I think my camera wasn't recording. Basically, when we draw our mean value here, so this is the bit that we plot, maybe in this case it was 10.5, the error bars are going to be equal to half of the range of that data. So for this point here, the range was 1.4, and that means each error bar is going to be plus 0.7 or minus 0.7 from that data. What you can then do is when you've actually got the error bars, you can then draw in your line of best fit. Now, a lot of the time this is going to be straight, so make sure that you use your ruler. It doesn't always have to go to the origin, but it's often good practice to put the line of best fit back to the y axis here, because sometimes we need to actually work out the intercept, and that might have some relevance. So over here, I've got my line of best fit. So I'm calling it the LOBF for line of best fit. That's lob off. And basically this wants to go, I guess, judging by eye through the centre of as many of these points as possible. When it comes to working out the gradient of a line of best fit, make sure that you draw a large triangle onto your line, and then very clearly show how you've got your y, your change in y, and your change in x values. People often make little mistakes just calculating the gradient, not forgetting, of course, that gradients can sometimes be negative as well. Now, the other line that I put on here is also a line, in this case it's a straight line, that still goes through within the error bars. And this one here, if this is like where it should be, we could maybe think, okay, does it go up? Is it steeper? Could it be shallower? This is my worst acceptable line of best fit. So it's still a line of best fit. It's still a good line, but it's not as good as it could be. And this one here, this worst acceptable line of best fit, is basically up to you to decide where that goes. Now, the reason we do this is that we want to actually quantify the uncertainty in this data. So what we can do is actually look at the percentage uncertainty in the gradient. And we do that using this equation over here. We can basically say that the uncertainty, the percentage uncertainty in the gradient m, well, it's going to be equal to the value of the line of best fit. So the gradient of that, take away, or the difference between that and the gradient of the worst acceptable line of best fit, divided by the gradient of the line of best fit. Now, sometimes we might have a shallower or sometimes a steeper worst acceptable line, and therefore it's just the difference in size between these two things that we're interested in. By putting these lines at each end, this is what we call the modulus. So we're just taking the positive value of the difference between the best and the worst divided by the best. Obviously, you then multiply that by 100 to get it as a percentage. We can also do the same over here, because over here we'd have our y-intercept, and we can then look at the percentage uncertainty in the y-intercept c, and that's just going to be equal to the value of your good y-intercept from your line of best fit. We take away the value of the intercept from the worst acceptable line of best fit, divide that again by the value of the good one, take the modulus of that, times it by 100, and then we can work out the percentage uncertainty in that data as well. Now, suppose we have lots of data and we've looked at percentage uncertainties in our measured values. What we can then do is actually combine this. So we can look at the combined or final uncertainty. Now, one way we can do this is by looking at the absolute uncertainty. So perhaps we know that x is equal to y plus z. Then the absolute uncertainty in our value of x is going to be equal to the absolute uncertainty in y plus the absolute uncertainty in z. So perhaps this is 10 millimetres plus or minus 1 millimetre, and that's 20 millimetres plus or minus 2 millimetres. Well, that means the final uncertainty is going to be the 1 millimetre here plus 2 millimetres, which gives a final absolute uncertainty of 3 millimetres in this piece of data. But we don't tend to do that very often. What we're more interested in is the percentage uncertainty in our final value. And we do that by basically thinking about what the equation we might be using. So it might be V equals I times R. It might be, a real physics equation. But I'm just going to say that maybe we wanted to find out the percentage uncertainty in X. And we've measured the percentage uncertainty in Y and the percentage uncertainty in Z. And to find X, we multiply Y by Z. Well, the final percentage uncertainty in X is going to be equal to the percentage uncertainty in Y added to the percentage uncertainty in Z. Okay, so whatever the uncertainty is here, we just add the percentages together. So it might be 2% and 3%, and that means this would have an uncertainty of 5%. Now this is just a kind of rough calculation. It's a way of guesstimating what it might be. But this is the method that we use. If we had maybe y divided by z, well, the uncertainty in x, because we've got a y term and a z term, again, we just add those percentage uncertainties together. And it's just kind of giving us a rough value. If x was equal to y squared, effectively this is just the uncertainty in y and the uncertainty in y again. So here the percentage uncertainty in x would be equal to the percentage uncertainty in y multiplied by 2. If x was equal to y to the power 4, the total percentage, the final percentage uncertainty would be the uncertainty in y multiplied by 4. And if we do this, this just then gives us a kind of an idea of what the uncertainty might be in that final value. And if you know the value of x and you know the percentage uncertainty in it, we can then use that data to work out what the absolute uncertainty might be. So it might be that we've then got an uncertainty of maybe 6 volts plus or minus 0.82 of a volt. So we can actually work out our final absolute uncertainty in our value based on the percentage uncertainty of the thing that we're using to record it. But this thing here hopefully makes sense and is going to be quite useful for you. So that's a lot about measurement. And actually there's a very final part of this topic, and that's looking at estimation. And what we're really talking here about is, can we estimate the size of a final answer by basically having a good understanding of the size of things that you might come up with in A-level physics. For example, you might know, for example, that if you're having to do estimates to do with the wavelength of light, we know light's going to be about 10 to the minus 7 meters in terms of its wavelength. If we're estimating the mass of a planet, it's going to be maybe 10 to the 24, like the Earth, or maybe the Sun is 10 to the 30 kilograms. Now, the more physics examples you do, the more these numbers will come up all the time, and you'll have a good understanding of lots of these. An example might be maybe calculate the force exerted on a car if it takes 4 seconds to come to rest. So what force is being applied to that? Well, we might think, okay, we don't know the size of the force, we know the time, but what else do we know, or what can we estimate? Well, we might estimate that the mass of a car is maybe 1,000 kilograms. How fast was it going? Maybe it's going at 20 meters per second. So maybe these are kind of the kind of average, the values that you might see from your calculations. You then might think, okay, well, we know that force is equal to the rate of change of momentum. So that's just Newton's second law. So that means the force is going to be equal to the change in momentum. So mv, which is going to be 1,000 times 20, so that's 20,000, divided by the time of 4, which is then going to be equal to about 5,000 newtons. So all I'm doing here, okay, don't worry about the physics so much, is all we're doing is kind of guessing or kind of just recognizing some kind of common values that we might get for everyday situations. You know, the mass of a person, the height of a building, stuff like that. But there we go, that is just a brief revision summary of the AQA measurements and their errors unit. This is going to be useful for every single part of A-level physics. Again, if you'd like to subscribe on YouTube, please do so. You can also pay to access hundreds more videos on my website, which I know will really help you as you prepare for your really important final exams. Until the next video, thank you very much. Don't forget to like this video and share it with your friends. Thank you.